Welcome to AI4C, Artificial Intelligence for Clinicians. This is our monthly series that is put on by the Mass General Brigham Data Science Office today, Thursday, October 13th. And we are delighted to have Dr. Synho Do, who's our very own from Mass General Hospital and Harvard Medical School. And he's got a really great topic to talk about today, and we'll introduce him fully in a second. People continue to log in. Those of you who are returning know this, but new folks, this is every second Thursday of the month from September to June. We take off July and August for folks who are on vacation and so forth. Last month we had Dr. Charles Kahn, Chuck Kahn, who is the editor of Radiology Artificial Intelligence, and he's from the University of Pennsylvania. And today, as I mentioned, we have Dr. Synho Do, we have Judy Gachoya, who will be in November, and then Omar Arno from Brigham and Women's. And those of you who are interested in viewing past recordings, we have all of them that are from our website. You can go to https://datascience.massgeneralbrigham.org, and all of the recordings are there for you to click on. Also, at the end of the session, please fill out a survey. There'll be a link in the chat. There'll be a link also in the chat to the past recordings if you're interested in that. But please do fill out the survey so we can continue to improve these sessions for you and give you things that you're interested in. You can go to our website, the Data Science Office of Mass General Brigham, anytime. Again, datascience.massgeneralbrigham.org, and go under educational activities. You can see it outlined here. And there you will see this icon for the Artificial Intelligence for Clinicians lecture series. And that's where you can find all of the recordings. There's the barcodes here, the QR code that you can use. You can also follow us on LinkedIn and on Twitter. But today, let's introduce our speaker. We're delighted to have Dr. Synho Do. He has a Master of Science in Electrical Engineering in Crypto System Analysis and a PhD degree in Biomedical Engineering, where he specialized in nonlinear biological system analysis. These were from University of Southern California. He was an NIH T32 fellow, where he received clinical training in cardiac MRI, PET, and CT. So he got experience in that. Then Dr. Do built his team of scientists, clinicians, and mentors at Mass General Hospital, Harvard Medical School, where he is currently the director of the Laboratory for Medical Imaging and Computation. He's currently an assistant professor of radiology at Harvard Medical School, and he's the assistant medical director for advanced health technology engineering, research, and development within the Massachusetts General Physicians Organization. His research interests are in healthcare data, machine learning, high-performance computing, nonlinear system identification, complex system modeling, and clinical workflow understanding. Dr. Do has carried out really impactful research in developing AI algorithms from messy data and validating results in the clinical environment, among other work. But today he's going to talk to us about a very interesting topic, explainable AI. And the title of his talk is Explainable AI for Transparent and Real-World Performance Monitoring. Dr. Do, thank you so much.
Thank you for your introduction. So let me share my screen. Can you see my screen? Yes. Thank you for inviting me. Today, I'm going to talk about explainable AI for transparent and real-world performance monitoring. This is a very interesting topic for clinicians and also data scientists. So today, this lecture will explain how explainable AI differs from the black box model AI or system identification method. And also, you will be able to understand how to develop new and additional features using explainable AI algorithms And also you will be able to understand how to develop explainable AI that can be deployed in the real world. So there are many definitions of artificial intelligence, but I like this definition. The theory and the development of computer systems able to perform tasks that normally require human intelligence, such as video perception and speech recognition and decision making and other language model development and translation between languages. So let me tell you about a little bit about the system identification. The terminology black box model came from this system identification. This is not a bad terminology. The motivation of this black box model is we really don't know anything about this system A. That's can you see my mouse here? So system,
yes,
yeah, thank you. So we really like to understand system A. To understand this system A, the conventional, traditional, the theory and technology was we use input and output sets. Here, X and Y, we can predict or identify system A. But in general, we don't know how complex this system is. That's the main reason. This is a linear system, linear time invariant system. The unknown system can be accurately modeled with n different measures. However, we don't know n. That's why many people ask how many data sets we need, how many parameters we need to estimate. Basically, we don't know. So that's why we just try to understand how many n might be inside of this system, and could be the complexity of a system or the in traditional system identification model called the transfer function. If we could estimate, we can burn that system transfer function as a chip so that we can implement this in the electrical systems. That's why this system identification was popular, and also people try to understand this system A as a black box model. This is a kind of a traditional linear system identification method. But later we learned that there are many nonlinear systems out there. For example, human functions and how human retina works, or how the hippocampus, the neurons work, and people try to estimate how the cells in the hippocampus, so that if we could model the hippocampus cells, we can improve the memory. So people try to estimate those human or the living cells. So those living cells are not linear. Usually, this task that normally require human intelligence, this is not a simple task, right? It's a complicated task. Human can do many, many complicated work. So when you look at this linearly separated model with just a line, you can separate red circles and blue squares. But in this, the second one, the not linearly separable model, the cases, we cannot separate the red circles from blue squares, so that we need a kind of non-linear boundaries. So because of this, or the same similar cases, because of this red circles forming a cluster inside of this blue squares with the lines. Usually the line is the decision boundary for linear system. With the linear system, we cannot separate these different cases for the nonlinear system. So simple task is usually linear. We can handle with a linear model. So conventional transfer function method works very well, so also very efficient. But complicated tasks like human intelligence level tasks, most of these tasks are nonlinear model. So traditional mathematical methods we try to use to model this nonlinear system. Those examples, the examples are Volterra series model. This is mathematically model this unknown system, black box, still black box. Then and high order statistical model we use to handle this nonlinear system modeling. One of the approach people started looking into is a neural network model. So when I was in the PhD students, we had only 3-layer neural network model. With those model, we couldn't do much compared to other general Volterra type of nonlinear model. So let's assume we decide to model this black box system with a nonlinear model. So we just decided it. Nonlinear model includes linear functions when the nonlinear components become 0. So when we don't know what kind of internal functions or the characteristics inside of this system, we can just assign the neural network model. This is actually what we are doing right now. So when people decide to model their AI functions, they decided to use a nonlinear model. And also they choose one of these network topology based on the specific functions or specific target the applications. But in general, we cannot find the best model. What kind of model might be best fit to my problem? We don't know in general. So that's why people try to use auto machine learning. They apply multiple network topology in this linear model, then use input and output pairs and try to estimate this number of unknown parameters. If we could estimate this number of unknowns, we can assume this system was well-trained so that we can test with a totally new data set. So we haven't used the new data set for the training. So this test data set, we can apply to this nonlinear system. Then we can take a look at the performance. But surprisingly, this convolutional neural network we use, and it's a lot of applications, they adopt this methodology. Actually, when we just decompose and then look at each components of this convolutional neural network, this is a multi-resolution filter banks with a hint of non-linearity. So without this nonlinear component, I'm going to talk about this activation function later. So all this natural image as input and go into the convolutional neural network and pulling hidden layers or pulling layers. This is a multi-resolution filter banks. This is just linear functions. The only nonlinear function is this activation function. This activation function is in between these filter banks and the downsampling and upsampling. So the non-linearity comes from very simple idea. So when the signal is becomes a minus, turn off the system. So we don't use this system. When the input X neuron activity becomes a positive, we turn on. So basically, this idea comes from the scientists. They try to mimic the biological system. It's like an action potential. When the chemical balance becomes increased to higher than specific threshold, the neuron turns on, the action potential starts firing. Those kind of ideas was adopted in this action. That's why the name of this function is activation function. When the threshold changes, the system turn on, otherwise turn off. There are many variations here to improve the performance and make the system robust. But basically, this convolutional neural network is a overall linear function with a hint of nonlinearity mapping. So multi-resolution function comes from global and local scope decision mechanism. And also another one, the filter banks means feature selection or signal selection mechanism. And then the final nonlinear activation function is a decision when neuron will be fired or not. So basically, this is very similar to our biological system. Then why this is a convolutional neural network is different from the we had a conventional machine learning algorithm and approach. It's called the computer-aided diagnosis. So compared to computer-aided diagnosis, so what's the difference in the convolutional neural network is we don't need the domain knowledge actually. So for the conventional machine learning, we need the domain expert. Somebody can, in this example, we want to develop the function detect a bicycle. Okay, the bike, how we want to develop a bicycle detection algorithm. In this case, we need the experts who understand bicycle very well, so that he understands bicycle composed of wheels and frames and pedals. So he just developed feature detection algorithm in his code or his model, so that when the new input data comes in, his the feature detection algorithm identifies those features, and then they make a decision. So that this is a human crafted feature plus data-driven classifier. But still, we need a human expert, domain experts here. But in the deep learning and the convolutional neural network, people believe that, I have a different opinion, but people believe that we don't need the domain experts. We just need the domain knowledge for data. So basically, we just need millions of bicycle images, then we can train the model. This model is pre-selected. We don't know what's the optimum and best model at this point, but we just chose one well-known open source data set, open source algorithm. Then we just curate our data, bicycle data, and train the algorithm. Then after we train the algorithm, so that means each node and each parameters are kind of estimated using the optimization method. This process is optimization method. There is no exact solution. This is all estimated solution. Then the new image comes in, and based on the training, this neural network decide this is a bicycle yes or bicycle no. So this is a data-driven feature plus a data-driven classifier. So when we want to, because of these characteristics, when we want to improve the performance for computer-aided diagnostic algorithm, we need to improve human knowledge. We need to understand the bicycle better, so that we need to redevelop new algorithm, better algorithm. So the results contains clear human intention. So human wants to detect each features. Oh, I want to detect this circle. I want to detect this frame. Different bicycle has different types of frame. Then I also include those different shapes of frame detection algorithm here, so that my algorithm could be improved. So that's the way to improve the computer-aided diagnosis algorithm approach. But in this convolutional neural network and deep learning approach, we just improve the quality of data, not also quantity of the data. If we increase the number of well-curated data set, we can improve the performance. The problem is when we just curate this data set, what if the animal images or cars and those non-bike images included in this training data set, so we cannot guarantee that our performance is improved. So that the quality of data is the key to improve the performance of deep learning algorithm and convolutional neural network. Again, the improve the performance, better data collection is necessary. So we can keep adding the new data or keep cleaning up the data. But the problem here is whatever the situation, the answer is derived. This is the big problem for this black box type and the convolutional neural network approach. Let's assume we have a number of unknown of a network is 1 million number of unknown, but we only have 1,000 data set. Then this data set is not enough to estimate properly the train this algorithm. But we don't know. So we only know what's the right correct the proper number of data set. So also even though we include the increased number of training data set, so we are not sure this training the algorithm is like paying attention to my intention. So my intention here our intention is train the algorithm. Okay, please detect the bicycle. But what if this algorithm detects a human instead of bicycle? So those kind of the unintended learning is we call the shortcut learning or confounding variables. So attention is very important in neural network training. And for example, I like to train we have multiple images. So this is car, this is boat. I like to train the model using this car images and boat images, but this is my intention. But what if the AI algorithm just pay attention to this roads, the mark, and also this light reflection on this images. Then in this new image comes in, oh, this is a car, not, because I learned this from this image, this is a car image, so this is car. Actually, this is boat, and of course there are cars, but this is a boat because I learned, this, the features in this image. This is a boat. What I try to say here is we need to make sure our intention was kind of captured in this AI algorithm. Actually, the reason I spend the time to explain this long is this is the main idea. We could publish this Nature Biomedical Engineering paper, so using explainable AI algorithm. So the question is, we want to train the AI so to identify and detect the intracranial hemorrhage and classify 5 different types of hemorrhage with a small data set. But how can we confirm and double check and AI really followed our training process and based on our training data set? So explainable AI is AI equipped with the tools that allow humans to verify that what they have instructed the AI to do. So it's a the complicated description, but in other words, we human wants to double check AI did pay attention when we trained them. So I trained you to detect the intracranial hemorrhage, So this is a conventional neural network, and this is different types of hemorrhage prediction. So the bottom functions that we developed to double check. So AI is really paying attention to our training direction. So the way we double check AI's attention is we develop automatically generate this atlas book. So we generated this atlas for each subclasses of intracranial hemorrhage. Then later we capture the most similar images from the training data set. So we can double check AI is really paying attention our training. This is a real data set we applied on the non-contrast CT. So when we look at this, this is a slice, G slice, the slice number. This is a probability, and different color means different subtypes of hemorrhage. So in this case, this is a slice 15. Slice 15 is a test data set. We didn't use this image for the AI training. So this is a totally new image for AI. And then the AI predicted saying this is a subechonoid hemorrhage, 99% probability. So here, so 99% probability. So here, then this part is the AI's explanation. So I think this is a subechonoid hemorrhage because you trained me using these images saying subechonoid hemorrhage. Then I think that this new image is very similar to this image. So basically AI just present the evidence, most similar 9 images taken from the training data set. It automatically go back to the training data set. Hey, these are all the similar images I learned from you. Then is it correct SAH? And then this is the nearest the features, actually images. It automatically retrieve. So human can verify that. Oh, probability is 99%, but it's good. But also these all the training data set AI retrieved from my training correspond to the SAH. So this is the process we validate, double check these different types of show the evidence by using this prediction basis. This is slice 17. As you could see, this is 17 has 2 different kinds of the hemorrhages. This is a subechonoid hemorrhage, 43% probability, and interventricular hemorrhage, 87%. But how do we know AI is doing the proper prediction? Because AI automatically retrieved these training data set we used to train this AI, then show us as evidence. Oh, I paid attention to your training, right? This is Atlas-based explainable AI model we developed. But this Atlas creation can be used as a tool to verify the performance of model. This is like additional function, not only just the conventional method. This is a 99% prediction probability or 85% of a prediction probability. This Atlas creation was a great approach to summarize and organize training data set. So initially, we wanted to use this Atlas creation to make the AI algorithm show the evidence of its, the prediction. But later, we realized that this way we can re-examine our training data set. So because this is, AI was trained using the training data set and estimated the parameters. Those parameters are real value, right? But still, the training data set is more important in some cases. So we make training data using only the data allowed for us, there is no chance to check the quality of before model training. What I try to say here is when we try to develop model, we don't have opportunity, we don't have a deep understanding what kind of training data set we need to curate. We just use as many as training data set. We just use training data set we have, right? So I need different types of training data set, but if we don't have those kind of data set, we cannot use for our training model. So through this Atlas curation, we were able to improve the performance later because we are missing specific features for specific labels. This Atlas creation is also available for educational use. So when we train the AI model, the AI performance is very good, 95% or 98%, but this Atlas could be used for the future training. The idea came from our earlier achievement, the bone age assessment model development. Radiologists might understand this very well. When the radiologists practice this bone age assessment practice, they use the Atlas book. They use the reference. So we adopt this idea in our explainable AI model development. Another very important the factor we need to understand in this AI model research is model characteristics function. In many papers and in many studies, they don't show this prediction probability distribution. So let's say, so model A has this kind of probability distribution. This is a positive prediction. We want to detect cardiomegaly. So this is a positive prediction distribution. This is a negative prediction distribution. Negative prediction distribution means there is an image. We say, oh, there is no cardiomegaly. So this is a probability of negative prediction probability. So another model B has different shapes of prediction probability. So in this case, same location. Let's say the new image comes in. The AI model says this is a 97% probability, but no algorithm say negative prediction probability these days. So we come up with this idea. We like to make sure how much this algorithm sure this is not a positive, so that we show the both positive and negative prediction probability. So if you have a 97% positive prediction probability with a negative 4% prediction probability is better than this positive 95%, zero negative prediction probability. I prefer model B rather than model A. So another case, this is a positive 90%, but still it has a 8% of the negative probability. There is a chance to be wrong, but here positive probability is pretty low, 45%, but there is no chance to be wrong. Each model has different performance characteristics. So each model means each label and each algorithm have this kind of function, but we don't test this model characteristics function these days. Do you check these performance characteristics in your model development? In many people, they don't check these functions. Can we change model A to model B? That's our goal. So this is a real world data set. We applied the same concept on our chest X-ray study. When you look at this cardiomegaly and pleural effusion, pneumonia, and pulmonary edema cases, these are 4 different cases using our institutional data set. As you could see, cardiomegaly and pleural effusion and pulmonary edema is well separated. Positive and negative prediction probabilities are separated. But when you look at this pneumonia cases, this is kind of confusing and mixed. Why this is happening? This is well correlated to our expert, the 7 radiologists annotation study. So cardiomegaly cases, this is a pairwise kappa statistics between 7 radiologists. The diagonal is the self-correlation. The off-diagonals are the cross-correlation between radiologists. They agree most of these cases, but here in pneumonia, they disagree. That means the pneumonia cases, its inter-rater variability is higher than cardiomegaly cases. In other words, detecting cardiomegaly is easier than detecting pneumonia cases, higher confidence. So there are many boundary cases. In explainable AI approach, it should be possible to describe the characteristics of each output of each model. Actually, these characteristics came from one model, one AI model, but we can examine each labels in individually. So even though AI performance is AUC, and in general, we try to use a global metric. The metric used to train the model is insufficient to explain the AI model. This is one big challenge in this black box approach AI development. Most of performance metric we use here is area under the ROC curve and sensitivity and specificity, precision we call, those are global metric, not the individual metric. So as you could see here, cardiomegaly and pneumonia detection has a different characteristics even in single AI model. After creating a model, measuring how each model component behaves is critical. So as we could see here. So, and also we try to understand this interrelationship between each labels. For example, let's say pulmonary edema. This is based on our NLP and our training data set. So pulmonary edema is well correlated to pleural effusion. So that means pulmonary edema and pleural effusion could be confused in terms of training data set. This is based on our training data set. So pleural effusion could be somehow correlated with foreign body. So kind of different kind of tubes or foreign bodies, and maybe the surgery or maybe the treatment. And also pleural effusion is correlated with atelectasis and pulmonary edema, pneumonia. So these are all the labels we try to understand through the training data set. People talk about radiologists or our doctors' practices like AI cockpit. So many data sets here. So we try to explain all our findings. For example, the AI scoreboards and the distribution of confidence probability and all the similar training data set retrieval. But this we cannot go on detail because this is under revision. But to use our additional metrics, we want to help our the AI model and the practice better, and the understand better and develop better. But there is something we don't mention in this community. So the problem is we don't mention that in many cases these models are not reproducible. For example, model initialization is a kind of random number generation. So it's very hard to keep the same random number. On purpose, we can do it, but in general, we just generate the model initialization with a random number generation. We cannot replicate the same model development with the same data set, also with the same model network. Also, the optimization method is it's kind of additional nonlinear operation, so that when the model is not initialized properly, the data set and networks are also same, but optimization method makes the process very different. Also, stopping rules are totally different for each trainer and also the scientist. So performance criteria are different. So most AI algorithms, the performance of each model created with the same data, the same algorithm, but still, the final product is different. How can we monitor the real world performance of AI model then? The problem is that the metrics we use are chosen for the training data and model selection. So the metrics we use in this AI research, those are for the training, not for the explaining the training data set and the test data set. So when we use AI model, we need to tool or new metric to verify that it works correctly on each new piece of data, not for the global or general data. We need the new metric to identify specific characteristics of each new data. So that's why the quantitative measurement should be possible even with the new data and different environment. This is another Nature Communication paper we could publish recently using the chest X-ray images using the quantitative metrics. The key idea here is the black box AI model is a human intelligence. So human, the scientists, they curate the data set and select the model, and they use open source, convolutional neural network, and they generate the prediction and probability to optimize their model. So no individual error control here. So it's very hard to find the cause of the problem because we just follow the optimization solving the optimization problem. And also very difficult to deploy and expand to new data set because we don't have any quantitative metrics or controls here. But we have tools in Explainable AI so that we could develop and test the human agreeable metric. So we have the same data set and similar algorithm, but we could come up with the human agreeable metric, and then we can apply this real world performance monitoring is possible. So specifically, we try to use this new metric for the auto labeling for the open source data set. So also we can develop zero error tolerance model, also possible to deploy to new data set. So this is two key the key idea we developed in our quantitative metric. One is patch similarity metric. So as I described before, so when we train the AI model, we can generate collect the atlas book. Then we also display this in the UMAD. Then we realize that similar image patches and similar features are clustered to each other, so that we can calculate the similarity, patch similarity through the normalization. So we can generate the metric. So what we are trying to calculate here is a new image comes in, then we can calculate the similarity to the training data set so that, oh, this new data set is very similar to our training data set. If it's not true, then, oh, this new data set has a very different features and very different structures, so that we are not confident enough to make a prediction. So it's the same idea. Another one is we like to look at individual characteristics of each label, so that we combine positive and negative prediction probability so that we can generate the metric. So, for example, cardiomegaly, this percentile, so that it's a kind of normalized ranking. So this is a ranking 11 out of 100. Negative is ranking 99 out of 100, means very confident this is a cardiomegaly. But the same data set, we detect for the pneumonia cases. So we could see, oh, I'm very positive this is a pneumonia, but also I'm really, I'm not very confident that this could be. We cannot easily rule out this is pneumonia. It's a kind of it's confusing cases. We try to combine these two concepts for the human agreeable metric. We call this a probability of similarity, PSIM. PSIM is a harmonic mean of a patchy similarity and confidence. So here, general neural network we develop, we form an atlas book here, and also we calculate the dual probability function. Then we combine these two metrics. Then we when you look at the different types of the mean, harmonic mean is 2AB divided by A plus B, and this is arithmetic mean, and this is a geometric mean. There are many different types of mean, but why don't you look at this trend? When we have an ultimate case, harmonic mean is try to the compensate or prevent the worst errors. So in this trend, so harmonic mean can be used when we want to average two different units or two different ratios. So that it's like F numbers is a harmonic mean of recall and precision. So it's more like a robust mean. So this is a real data analysis. When we applied only confidence probability and we only apply the patchy similarity, we have this kind of threshold. But when we apply this PSIM, this is harmonic mean of these two metric, it's more like consistent. And ultimate cases like a pulmonary edema, this is very confident cases. But in terms of patchy similarity, our explainable AI think, oh, this patch is not that similar to our training data set. Even this kind of cases, PSIM is more like less fluctuate and more consistent performance we could get. So pleural effusion, as you could see, the confidence probability and patchy similarity can be combined to form a PSIM here, and pneumonia. So it's a very high threshold, means it's very hard to find the similar high confidence cases. Also, this is not easy to find the similar patches, but PSIM is more like this is based on the real world test from 7 radiologists, so that this is blue dots are false positives and true positives are red dots. So we confirm that this PSIM works very well and robust. How PSIM can be implemented actually? So PSIM is a human agreeable metric. Then one of the example we applied this PSIM is we develop our explainable model and calculate the PSIM with the quantitative metric, and then we apply this PSIM concept to all the open source data set, ChestPert and Mimic and NIH. This is a number of cases, and PSIM implemented to evaluate each data set with this quantitative measurement, so that we can automatically label these cases. This is a little busy, but when you look at this PSIM value, higher PSIM means AI is very confident. This, it can automatically label. Then A, B, C, D, E, F, G, H, G is all human radiologists, and GT is ground truth. This we use a majority rule so that even AI is a higher PC means very confident this is cardiomegaly. So this is when we increase the PCM, there is a negative cases. This is all the negative cases. So when we increase the PCM, AI is very confident this is negative cardiomegaly. There is no cardiomegaly. But when the PCM is low, so this is ground truth, human experts ground truth. So there is a kind of error. So what this means is by increasing the PCM value, we can find the threshold. AI doesn't make mistakes. Also, AI is well aligned to humans' opinion. So cardiomegaly is, the humans agree and AI agree very well. So even smaller PCM, so there is no error up here. This means that when we increase the PCM value, the number of capture cases decrease because we increase the PCM, but correct capture rate is consistent and very high because this is an easier decision for even AI and human. But pneumonia cases, when AI predetermine these PCM cases, higher PCM means AI is very confident this is positive pneumonia cases. This higher PCM on this negative, AI is very positive, confident there is no pneumonia. But based on human experts, this is a consistent and well, correlated to PCM metric. So even though this is ambiguous and difficult cases, AI can be applied in individual different level for cardiomegaly and pneumonia. Then we can automatically label, the open data set. So we can apply the PCM value to each class individually. So as we could see, cardiomegaly is easier to automatically label compared to pneumonia cases. And for high conspicuity clinical output level, like cardiomegaly or pleural effusion, so even human radiologists agree, most of those cases, we can use a low PCM, then also high auto capturing is possible. For more subjective, non-specific clinical output level, like with a lower inter-rater agreement, we can increase the threshold on PCM so that like pulmonary edema and pneumonia cases, we might have to increase the PCM, but still we can automatically capture because we know that where is a threshold that this quantitative metric. So atelectasis is a lower conspicuousy cases, but more also more non-specific clinical label typically noted that chest X-ray reports only when it is present, but not mentioned when it is absent. So because of this reason, we could see this trend. For example, this is a positive prediction PCM. Most of this cardiomegaly, we can capture almost 90-something% accuracy. For negative prediction value, it's a little higher. But pneumonia cases, even though positive prediction value, we cannot capture many cases automatically because of many ambiguous cases. Around 35% of automatic capture is possible. But for the negative prediction value capturing, for example, there is no pneumonia automatic capturing, we can increase the 1 minus PCM is increased. This is a new metric. So today I try to explain what's the difference between a black box AI model and explainable AI. So I have to explain the fundamental ideas and try to connect to the real world application. So the metric used to train the model is not proper. for the real world use, because those metrics for the model training, not for the using those model in the real world. So new metric, like for example, PSIM, that quantitatively describe the relationship between training data set and new data set. So that's why this new metric can be used in real world AI model. So for the real world deployment, it must be developed with the explainable AI. That's why we can develop this quantitative metric like PSIM and other similar approach. Thank you for your attention. So if you have any question, please send me an email or you can ask a question right now.
Great. Thank you so much, Dr. Do. That was very, very interesting. You know, you started out in telling the difference between traditional CAD, computer-aided detection, which used human-defined features, and sort of the other extreme of a CNN that doesn't have, sorry, cat is getting away, that doesn't have human-defined features, is more data-driven, and really shown that maybe the combination of both those things is really what we should be doing, adding back in some of the human intelligence that we're aware of with the abilities of CNN. So that was really fascinating. We have a couple of questions here in just a little bit of time left. One attendee asked, could you please tell us how were the optimal probability thresholds for positive and negative determined in order to get good separation of class labels?
So this is a good question. So there is, usually we think there is one single threshold to determine this is positive and negative when we use only one probability distribution. But when I showed you the dual distribution, we can use a dual threshold. So we can determine two different thresholds.
Got it. Okay, thank you. And another question here, did you have class imbalance problem and how do you overcome that?
So this is a big problem for the real world data processing. So we like to have balance the data set for the model training, but we don't have access to those very rare cases. Then there is no way to improve it. But there are multiple ways to overcome this, but that's not a real overcome. That's a kind of mitigate the effect. For example, data augmentation. We can do multiple data augmentation, rotation and translation, and zoom in and zoom out. But the thing is, when we use explainable AI, if you remember that data, the prediction probability metric, even though you train the model, you can investigate each data label. Oh, cardiomegaly, we have enough data set. The performance we can trust. For pneumonia, oh, this is based on this prediction probability model. Maybe the data was not good enough, or we didn't have enough data set for the training. So somehow the model couldn't capture all the features for the pneumonia, so that we might have to add more pneumonia cases for the next training. So, or maybe we shouldn't use pneumonia. When the AI say this is pneumonia, we might have to pay attention because AI can make a mistake. Because if we don't know this kind of explainable model, with this data imbalance, there's any way we can overcome. But if we use explainable AI model, because of data imbalance, our specific function is not working very well, then we can ignore or we pay more attention when we use in the real data set. So data imbalance is a big problem, but we have a solution or way to mitigate the impact in the real world of deployment.
Fantastic.
Explainable AI.
Thank you so much. Well, we've run out of time. I want to be respectful of your time, and I know you really stood up at the plate here. I know you're not feeling well today, but thank you so much for delivering this wonderful lecture, very interesting concepts and things we should think about and how we move forward with some of our work in AI. So thank you so much, Dr. Doe, for your presentation. Thank you, everyone. Fill out the surveys if you can, and we'll see you next month. Thank you all.
Thank you.